Hello, Mike Allison here with the next release of the X16 Assembly Environment. It's been a while since I did the previous release, and I'm trying to get functionality out so that people can play with it, and this is a rather important feature release. Previously, I concentrated on interactive editing of instructions, the ability to enter and delete instructions. And that was all well and good, but in the process of editing instructions, embedded addresses and arguments to some of the instructions would become invalid. And that's what this release is going to fix. It's a problem I call code relocation. And effectively, we're patching addresses inside of the live code so that it's still valid and will still work. What do I mean by code relocation? Well, let me show you what some of the problems are. One of the problems are absolute addresses. When you're using a 16-bit address, like with a jump or a jump subroutine or a load, that value can get changed if you move code around. Another address are relative addresses like you might find on the branch. Partial addresses, because this is an 8-bit machine, I can't load a 16-bit address all at once. I have to break it up. Those partial addresses can become invalid. And finally, I could have data tables with addresses in it. All of these problems need to be fixed during the process of editing. Let's look at an example here with 16-bit addresses. My main program doesn't do much, just calls a routine. And the routine, of course, doesn't do very much either, it just returns. The routine starting at 1004 is called correctly on that very first instruction, the jump subroutine. If I add some functionality to the routine, it doesn't change anything. The entry point is still 1004. But if I now add an instruction back in my main, everything gets pushed down, and my routine is now at 1005. And if you see at 1001, these digits here in the red are now invalid. That address of 1004 is no longer valid. And of course, it only gets worse as I continue to add instructions. What really needs to happen here is that the assembly language environment needs to patch those addresses so they're using the correct entry point. Another problem is relative addressing. You see here I've got a loop where I just call a routine and the entry point is at 1005. If I add something into the loop, in this case a no-op, that address FB, which is a negative offset, is no longer correct. Instead of going back to 1000, it's going to go back to 1001, and your resulting program would be trying to execute that jump subroutine's argument as instructions, which are almost certainly not correct. So of course what needs to happen is that the assembly language environment needs to adjust that relative offset and fix it. Here's a problem that takes more than just looking at the code. If I'm trying to load the address, in this case of my data word at 1000C, that address is broken into two high byte and low byte arguments, and then they're stored off into a 0-page register. Everything's well and good until I added some code and it pushed down my data. Instead of being 1000C, it's now 1000D, and you can see these red digits are no longer correct and they're invalid. And of course, what needs to happen is that the runtime system needs to patch it so that it's pointing to the correct data. This is a little more complicated because now we have to track that these are address expressions. This is not obvious based on just code inspection. And finally, well, it's not a code problem, it will result in your program not working. What about cases where I have addresses in data tables? In this example, I've got data 1 and data 2, just 2 bytes. They're stored in a table here at 1003, 1005. You can see the addresses are totally consistent with the previous definitions. If I then add some code to my main program, it pushes everything down. These address values are incorrect. And by now you've probably figured out what needs to happen. The assembly language environment needs to patch these and maintain it. Much like the address expressions in the previous example, this is a tougher problem because the assembly language environment needs to track this line here at 1003, and notice that the argument to that is an address expression utilizing data 1, so that when everything is pushed down, it can write the correct value back in here. And it needs to do this without any intervention on the user's part. That's the whole point here, is that trying to track all of that stuff is very difficult, and it's a lot of fiddly bookkeeping. This is a great chance. Let's have a live demo, and we'll write a simple program, a hello world program, and you'll be able to see this in action. Okay, so let's start with our live demo. One of the first things I'm going to do is I will turn on the mouse so I can point to things to make it easier to see what I'm talking about. When you're running this, you don't normally need to do it. So we'll load the assembly environment just from our default disk and give it a run. If you've not seen this before, up at the top, these are our different operational sections, and I will show those as we go along. The first thing we're going to do is create a new program. And because of where this is in memory, let's do it at 6000. Here we can see the program starts at 6000 and ends at 6000, so it's not very long. Let's go see what the program looks like. By using F3 and then choosing the address function, I'm going to start looking at the assembly code at 6000. You can see the main is only a return from subroutine. So I said we're writing a hello world program, and all hello world programs need a string for hello world. We'll put this in after the main program, and then using the F2 function for insert, I will insert a C string. I'll say hello world, and it puts in all the bytes for the string. You can see there's the H, E, L, L, O, space, etc., all the way down to the 0 at the end, like any good C string. I'm going to go back and reset my address to 6000, because remember I said I've got a limitation. You can't scroll backwards right now. So that's great. I can't refer to the string through anything except an address, and to do that I'm going to apply a label. So using F5, I'm going to insert a label, and I'll be very imaginative and call it str. Great. Now we're ready to begin writing some real code. Just for fun, I'm going to use the 40 by 30 mode on the Vera. And I happen to know that that is a mode called 0. Thing to note here is that right now all of the instruction arguments need to be in hex. A future version of the code will relax that, and you'll be able to do it in decimal. Great, there's the instruction, and now I just need to tell the system that we're setting the mode. And this one happens to be at FF5F. That's the vector that will set the mode. Super. Now, I want to clear the screen. that is a constant hex 97 character code, which will then proceed to print out. FFD2 is the vector to do that. So there, we've loaded the 40 by 30 mode, told the system to set the display into that, loaded the clear screen character, and printed that, causing the screen to clear. Final initialization I need to do is I'm going to load a color code, and for this particular version of the emulator I need to store it in a low memory location, and that will set the color of our text. So setting it to 6:1, background is blue, the foreground color is white, and that should be the color of our text. Now I've got to point to the string. I'm going to use low memory, 0 page memory, 0 and 1 as the pointer to the string. So I will now load the low byte of the string and then store it at 0. You see here the system remembers that I'm talking about string, but that's only the low byte, 15 in this case set, corresponds to the low byte of that address value. Do the same thing for the high byte. And store that in there. Great. Now I've got a register pointing to the string, and I need some way to index that. I'm going to use Y. So I'll initialize that by loading that with 0. And now I'm ready to actually start reading characters from the string and then sending them to the output. And I will load. Now this is an indirect indexed. That loads the first character from the string. And then I'm going to go ahead and send that to the output. $FFD2. That printed that out. I'm done with that first string, so I'll increment Y. And then I need to go back to my loop. It's not going to be able to find it since I don't have anything to find. Let me get out of that. Go back to the top here. Now where did my loop start? It started right here where I loaded the character. So let's put a label on that. Now I can go down here and I can say branch always to loop. That sends it back to the top. You know, I don't like that being called main. Let's get rid of that. Add a label, call that exit. And back at the top, I want to call this main. There's nothing special about main. It just helps me visually keep it clear. The only thing missing is I don't have the ability to exit my loop. Knowing that it's a C string, that last character being a 0 will tell me if it's time to leave. So we'll put a branch equal to exit. Now how are we doing? Oops, I see a bug. I was hoping we wouldn't see that, but if you look here, this lost the indication that we need to go back up to the top of the loop. So I will fix that before you get your hands on the code, so that won't happen. Easy way to fix it, just delete it, re-enter it. Now we're set up in there. How does that look? I think it looks pretty good. Okay, I'm going to get out of assembly mode and I'm going to try and run it. Hey, look at that. We got into 40 by 30 mode. You can see that the characters are much larger. It printed out my string, and now the assembly language environment is holding execution at the end after the program did its return. It's just waiting, and it's waiting for me to press a key to return back, and now we're back. So I ran the program. If I go and choose the view menu, I can actually look at the saved screen. Here's another bug. This should have set the Vera mode to fill the screen, but you can see this is the space that the 80 by 30 mode took up, and that saved that. And it's waiting for me to press another key, and we're back where we were. Still a few things to fix, and I'll talk about some more of the features that are coming in the next couple of releases. This release took a lot longer than I had expected due to several things happening. As they say, life happens, and I wasn't able to get all the features in that I thought were important for version 0.7. As a result, I'm planning on several smaller releases that are going to incrementally add extra ability that we haven't had prior to this. One of the big problems right now is that you can only scroll down in assembly view mode, and I want to add the ability to scroll backwards. The next would be actually saving the program to disk, along with all of that debugging information and the address expressions we talked about previously. Following on to that would be the ability to save your program as a text file. At some point, as you edit the program, it's going to be way too large to continue to do development in this style of interaction, and you'll want to save it to text, perhaps so you can run it into a more traditional assembler program with a more mature toolchain. We need to improve our error messages. Right now, the catch-all error message is invalid syntax, which is not always appropriate. I want to add error messages that help give you the information you need to figure out what's wrong and how to fix it. And as a stretch goal, I'd like to add into the debugger something that allows you to see the current state of the Vera interface chip. If you're ready and you'd like to download the assembly environment, go to this Google site and the instructions will point you to version 0.7. And please, if you can, send me feedback. Let me know about bugs. Let me know about features that don't quite work. Or if you're happy with stuff, I'd like to hear that too. Thanks for listening. Have fun.